Hello everyone and welcome back to the Jamaican Geologist YouTube channel. This is episode 6 in the Geology Foundation Series, and today we are extending on the minerals. So far in the last 2 episodes we have looked at how to identify minerals and how to classify minerals. Today we are going to focus on mineral formation. Specifically, we are going to focus on orogenesis. This is the last episode in the series dedicated specifically to minerals, so we are coming to a bit of a conclusion here. As usual, I'm really looking forward to it, and I hope you are too, so let's get started. Now, let's start with the basics. A theme of this series so far has been to break down complex terms and definitions. I thought it fitting for this episode to look closely at two terms which I believe are crucial in laying the foundation for what I'm about to talk about for the rest of the episode. The terms are mineralogenesis and orogenesis. So let's start with mineralogenesis. We see two words, mineral, we know what this is by now, and we also see genesis. Genesis means the beginning or origin of something, like how Genesis is the first book of the Bible. So based on this, we can say mineralogenesis is the origin, beginning, or formation of a mineral. All right, cool. We have that covered. So that's simple and straightforward. Okay, but mineralogenesis is a broad and overarching term. For this episode, I want to focus on orogenesis. Now, this is easy to break down too. I mean, we see Genesis and we know that this is the beginning or origin or formation of something, but what is an ore? Well, the word ore by itself is defined by the Oxford Dictionary of Geology and Earth Sciences as a mineral or rock that can be worked economically. There is also ore body, which it defines as accumulation of minerals distinct from the host rock and rich enough in a metal to be worth commercial exploitation. So orogenesis can be defined simply as the origin or formation of economically viable minerals. And I guess you can see why I have decided to focus on orogenesis for this episode, but I will get into it a little more in the next segment. Before I get into why I'm focusing on orogenesis, I thought it necessary to share an excerpt from Jan Zaliasevich's book, Geology, a very short introduction. It reads, and I quote, "The familiar world that we build around ourselves mostly comes from geology, in one way or another. The houses in which we live, the offices and factories in which we work, are made of reconstructed sand, gravel, mud rock, and limestone, with a few nicely polished slabs of granite or marble thrown in as decoration. Many of these constructions have an internal skeleton of steel taken from huge iron ore deposits formed near the dawn of our planet. And that steel is also an integral part of the tools we use and the cars we drive along roads that are long strips of crushed rock bound with bitumen. Other metals such as copper, aluminum, zinc, and lead add to those constructions, while yet more unfamiliar ones such as neodymium, hafnium, and europium are now crucial to the electronic devices of the computer age. We use immense amounts of energy, mostly taken from coal, oil, and gas in the ground, while part of that oil now goes into the plastics that make up the clothes we wear, the carpets we walk on, and the packaging around the food that we buy at the supermarket. Geological materials are utterly pervasive within our lives. So, how do geologists seek those out from within the crust of our planet? End quote. So, what is abundantly clear is that minerals are essential in pretty much all aspects of modern human life. This is a point I have emphasized throughout the series so far. So, in this episode, the emphasis is on orgenesis because I want to focus on minerals of economic importance, which via extraction through mining sustains modern human life as we know it. All right, we know what orgenesis is, but there are different types, as you will see in a moment. But even though there are different types, there are three fundamental characteristics, mechanisms, or processes that are key in pretty much every form of orgenesis. These sub-processes, if you can call them that, are source, transport, and trapping. Let's start at the source. I mean, the mineral has to form somewhere, right? There is a process happening like some mineral fluid from superheated water or high evaporation. You might remember evaporite minerals from our last episode. Or if you want to get extreme, the explosion of a star in some distant galaxy in the universe. And there are many other sources of origin. The key takeaway here is that something happened somewhere. All right, cool. Now that we have spoken about source, let's talk about transport. Often the areas from which we mine minerals are not where they originally formed, because often it is very infeasible or impractical to mine from these sources. It doesn't make economic sense. To get from areas of formation or source, there needs to be a mechanism or conduit for it to be transported. Often like a vent or crack in the rocks, forming mineral veins. Sometimes the mechanism can be a stream or river, and there are many other ways like tectonic uplift, volcanism. But the fundamental takeaway is that once it forms at the source, something has to transport it elsewhere. Finally, let's talk about trapping. In order for something to be considered mineable, it must be abundant or economic enough for us to say it's feasible to mine. I mean, there are other factors at play too, like legal stuff, governmental things, environmental sensitivity of the location, accessibility, like if enough proper roads lead there for haulage, among many other things, which we can look at in future videos on this channel. But one of the key things is there enough of this mineral in this place to consider it economically viable? All right, cool. But in order for it to be considered economically viable, something had to trap or keep enough of it for us to see the mineral in abundance. A good example I can think of readily is a river. The river, during its transport, picks up minerals from the source in the mountains. Here, the flow is high and the material is eroded away. Downstream, the land, it doesn't facilitate as much velocity in the stream, and the material is deposited because of the density of the material being too high for the stream to transport it. So, in other words, you can say that the mineral is now trapped here. Other ways are faulting or fracturing, structural traps. Now, structural trapping is mostly talked about in the oil and gas industry, but It can be applied to mineral exploration too, as you will see shortly. Having shared all of this, it may be a lot to process all at once for some, but the key takeaway here is that the mineral forms somewhere called the source or area of formation, and this source is often impractical or infeasible to mine. It is transported from the source by some sort of geological process to an area with the right conditions for the mineral to accumulate in sufficient enough quantities for it to be considered economically viable. So, have you ever stopped to think about how a metal like gold formed? I mean, yes, I know that gold makes jewelry. My wedding band is made of 14 karat gold, and I will explain what this means in another video. There are gold necklaces and bracelets, gold watches, even gold teeth. If you are really into electronics, you might even tell me that gold is in the circuitry of devices like my tablet and smartphone. If you're in the financial sector and really into investing, you might tell me that gold is a good hedge against inflation, so it's an excellent investment. All that is all well and good, but where did this shiny yellow metal that everyone gets excited about come from? Well, I find that a lot of non-geological sources like to focus a little bit too much on space and not how it works right here on Earth. They will go on about the astrophysical origins of gold. They will talk about an exploding star, something called a supernova. This explosion led to the interstellar dust, and as the early solar system formed, gold, silver, and other metals from that explosion became part of Earth. Okay, that's fine, and it is there is validity to it. I mean, there is gold everywhere on Earth. I mean, if you go outside and pick up soil right now, there is gold present. But there is a caveat though. Unless you live somewhere where there is an anomaly or you live in an actual gold mine, the amount of gold in Earth's crust is ridiculously low. The average concentration of gold in Earth's crust is about 4 parts per billion, or 0.0000004%. Not very economically viable at all. In water like the sea and oceans, it's even worse at about 10 parts per trillion on average. But we do have gold mines, right? And people explore for it all the time, right? How do we know where to look in the first place? And how did we establish these mines to begin with? This is where the story of gold formation on Earth begins. The process typically goes something like this. Long ago, and by long ago I mean, millions of years. Long ago, there is extensive volcanic activity. Magma would migrate from deep in the earth and move a little closer to Earth's surface, forming magma chambers. As the magma chamber fills with magmas, areas of weakness in the rock would form cracks. Sometimes, when the geological conditions are right, the magma fills the cracks, forming a vent, which eventually forms a volcano. All right, cool. We know what volcanoes are, but this isn't always what happens. We don't always end up with volcanoes. Imagine that volcanoes did not form, as the conditions were not conducive for a volcanic vent to form connecting the magma chamber to the surface. Above the magma chamber, there is groundwater. Typically, you have a water table which separates the zone of aeration, where there's no water, from the zone of saturation, where there is water in the ground. The groundwater works its way close to the magma chamber and it is heated to extremely high temperatures. And then that superheated water rises, filling in the cracks mentioned earlier. Near to the chamber where it really got hot, it dissolved minerals, and that superheated water with dissolved minerals enters the crack. As the water cools, the materials or the minerals are deposited through a process called precipitation. This is called mineral formation through hydrothermal activity. And you can kind of see why, right? The prefix hydro means water and the suffix thermal means heat. So essentially, we're saying the minerals form from hot water. Anyway, as the water starts to cool, the mineral deposits in the cracks, which eventually forms mineral veins. Various minerals are deposited in these veins, including quartz, pyrite, chalcopyrite, galena, and of course, gold and silver. A good analogy often used is the toilet and pipes in your bathroom. There is sometimes lime scale which builds up if the water has enough dissolved calcium ions. The difference here is that the water in your home is not superheated and the mineral deposited is calcium carbonate as opposed to the metallic minerals and quartz in the mineral vein. That's pretty much it. The key takeaway here is that metallic minerals like gold, silver, copper, lead, zinc, iron, and tin, among others, typically form as hydrothermal deposits where superheated water from deep in the earth deposits minerals in cracks, forming mineral veins. So metallic minerals are often associated with volcanic rocks. In Jamaica, a lot of the known metals like copper, gold, and silver are associated with the Cretaceous volcanics. The Cretaceous volcanics typically occur in geological spaces called inliers. The gold mine in the island, which was active in the early 2000s, was located in the central inlier. And I will talk more about this in other videos. I have plans to bring on a couple of colleagues who are more intimately involved with mineral exploration than I am, and of course, are more experienced and knowledgeable about this kind of stuff than I am. So you should stay tuned for those interviews. Okay, you may be familiar with panning for gold in rivers, or you may be familiar with the 2006 movie Blood Diamond, in which Djimon Hounsou's character found this beautiful pink diamond in the river when he was enslaved by the rebel army. Don't worry, I won't reveal any more of it in case you haven't watched the movie yet. Although it has been like about 20 years since that movie came out, almost 20 years. Anyway, the river is a common theme in those gold and diamond examples. These are called placer deposits. The Oxford Dictionary of Geology and Earth Sciences defines placer deposits as deposit of materials, example, gold, diamonds, tin, or platinum that has been concentrated by mechanical action. Placer minerals generally have high density and resistance and therefore may concentrate during various types of weathering. So here is what happens. You have mineral vein created in the hills by millions of years of hydrothermal processes like I described earlier. Or you might have disseminated deposits when the rock is a little more porous. Anyway, you have your high concentration of a mineral like gold or diamonds somewhere in the hills, which is remote and inaccessible for any human being or modern technology to reach. This is your source. Over time, this rock breaks down and the sediment is picked up and carried by the river and it's transported downstream. Downstream, the river velocity is not as high as it is upstream, and the sediment, including small amounts of gold, start to be deposited. Gold tends to accumulate inside the bends of rivers, what we call meanders. You may have remembered this if you did geography in high school. Gold also accumulates behind obstacles like boulders or in little depressions in the river. Okay, what I just described for you is what you call an alluvial placer. Alluvial means river, and alluvial placers are the most common type. And this type of placer is what you are likely to come across in the literature and the field in most places on Earth where there are placer deposits. But I think it's also important to note here that there are also aeolian placers. The word aeolian means wind or wind blown. And well, they are formed by wind action in arid and semi-arid regions as opposed to in water by streams. Right off the bat, I want you to know that porphyry deposits are associated primarily with copper. I mean, if you hang out with geologists who do mineral exploration long enough, you will definitely hear about porphyry copper, sometimes multiple times. Although copper is generally the most talked about, molybdenum bearing ores too form as porphyry deposits. And there is even gold enriched porphyry copper deposits. Anyway, put simply, a porphyry deposit occurs near subduction zones from magmas that have been oxidized. Um, they are quite similar to the typical hydrothermal deposits I described earlier. Some differences are that porphyry deposits tend to be larger than your typical vein deposits. They spread out more in the rock, whereas vein deposits are more concentrated. And in terms of grade, porphyry deposits tend to have lower grades but higher tonnage, and vein deposits tend to have higher grades but take up less volume. And I'll explore this a little bit more in other videos. So there are a few other forms of orogenesis that I wish to touch on here. There are volcanogenic massive sulfides, or VMS for short. These ores are associated with hydrothermal vents in submarine or underwater environments and yield metals like copper and zinc. Then we have orogenic gold deposits. So gold just doesn't form only in hydrothermal vents or are trapped in placer deposits. Gold can also result from the mountain building process or the orogenic process. And orogenic gold deposits are formed from compressional tectonics, and we'll explore that in other videos. There are also magmatic processes. As magma cools, crystals start to form, and well, a lot of the crystals we like are associated with cooling magma and metamorphism. Okay, as you may imagine, understanding ores in general is a lot. This list of orogenesis processes I just presented to you is by no means exhaustive. There are several models out there on ore formation and several other methods not discussed in detail here. There's also a lot of literature as well. If you open any scientific journal on economic geology, mineralogy, and geochemistry, these articles can be a lot to take in, even for someone with scientific knowledge and training. But I believe that this is enough for an introductory YouTube series. For the geoscientists watching, please feel free to comment and let me know if there is anything you would like to add. Are there any models or many models of mineralogenesis or orogenesis you would like to add? Drop me a line in the comments. I would love to hear from you. All right, so all this fancy sounding science and multiple syllable words we have to break down. Why does it matter in real everyday life to the general society? Well, understanding ore genesis helps geologists discover new mineral deposits by identifying the right geological settings and processes. And I believe you know where I'm going with this. As of the recording of this video, it's July 2025. We are coming to the end of the first quarter or so of the 21st century. We are now a massively technologically driven civilization. Electronic devices are a main part of the information and communication technology infrastructure. Cars are electric, medical devices are more sophisticated, and there are calls now to switch from fossil fuels to completely renewable technologies, and I can go on and on. Now then, with all these technological advances and demands, we need more metals, and not everything can be recycled. That means more exploration and eventually more mining at least in the foreseeable future, you know? So understanding the processes of orogenesis is absolutely critical as our technologically driven world becomes more interconnected and as we switch from fossil fuels to renewable energies in our fight against climate change. And I can go on, but I have echoed this sentiment or these sentiments a lot on this channel. And for those of you who watch regularly know exactly what I'm driving home. So, but don't just take my word for it, right? There are several media outlets and scientific papers reporting on this all the time. Now I must pause here to say special shout out to Margaret Artram and Hank Hedge. Most of what I learned about metallic minerals, my foundation in metallic minerals really, I spent time learning from them. So I hope I did justice to the topic, you guys. We have come to the end of this episode and the end of minerals in the series. In our next episode, we will talk about rocks. We started the technical part of this series with atoms, and we have spent the last 3 episodes on minerals. Now we are getting larger as we will start to discuss rocks. Looking forward to it. Until next time, it's bye for now. Take care.